in very first chapters, we learned about independent events. So we said that two events A and B are independent if probability of their intersection is equal to product of A probability of B. So if you could probability measure of intersection because product becomes probability of. Then we defined random variables and we say two random variables are independent if their joint density or joint CDF or joint characteristic function like fxy of x and y can be decomposed into fx of x times fy of y. Or for the, let's say, CDF, doesn't matter. Let's say if we write the CDF or PDF. So remember that when we talk about CDF, this is probability that x is smaller than or equal x and y is smaller than or equal y. And then this is equal to probability of x is smaller than or equal x and probability of y is smaller than or equal y. So this independence is not just independence of two events, but so many events, because for different values of x here and different values of y here, you will have lots of different events, and all of them, they should be. So the class of all these events should be independent of the class of all these events. So in that case, we call x as random variable independent random variable y. So remember that a random variable is not an event, but we can use a random variable to define different events. For instance, this is a random variable defined using, this is an event defined using this random variable. And this guy is another event which is defined using my second random variable. Now, here we want to see independence of multiple random variables. And this is just a simple generalization. So the definition is that we say a set of random vectors or a sequence mutually independent if all the events that are, the first one is only defined using x1 and the last one is defined only using the last one, are independent. That means that their joint CDF could be decomposed, or joint PDF or joint characteristic function could be decomposed. So if you write, for instance, this is the joint CDF of all these random variables, this is the marginal CDF of x1 times CDF of x2, etc. So if you have this one, instead of the joint CDF, you could have written the complementary CDF and so on. Because if this is true, so you could show that the joint complementary CDFs also is composable and this and that. From here you could conclude this one, and from here you could conclude. So these two are equivalent. So if the joint PDF of these random variables is equal to the marginal PDF of only x times and so on. And remember that this should be true for all x1, x2, etc. In real. So for all points. For example, if I say that I have an independent random variable, it means that the joint PDF can be written as product of the marginal PDF. So as soon as I say that they are independent, this is the meaning of that. Now, if you have these independent random, if you add them together, now what's going to be the distribution of the sum? So to answer these questions, this system is a system of equation, because this means that y1 is equal to x1, y2 is equal to x1 plus x2, etc. So you could have seen these as y1 equal x1, and then y2 is equal to y1 plus x2, and y3 is equal to y2 plus x3, and so on. So it's an accumulator. Because yk is yk minus 1 plus xk. So you add something, or in MATLAB you can use cum sum. So if cumulative sum. because you're accumulating xa on it. So it's kind of like you have x1, x2, and xk, okay, and then this is y1, and then you add this one to this guy, okay, add this, you get y2, and then you add this one to let's say x3, you get y3, etc., and then you get yk is summation of the previous one and the next one. So it's like you have k input and you have k output. So you have a transformation of k random variable. So if you write this set of equation and then try to solve it, so from here the solution for x1 is y1, and from here the solution for x2 is equal to y2 minus x1, so it's going to be this one. So yk minus 1 is xk. Remember that this solution xi or xk is written in terms of y1 to yk. So this is for any problem. So we have to write the inputs versus the output in order to be able to find the distribution of y in terms of x. Now here the Jacobian. So if you calculate the Jacobian matrix, so you have a matrix, derivative from here, the derivative of y1 with respect to x1 is 1, derivative of y1 with respect to x2 is 0, y1 with respect to x3 to x3, so you get lots of zeros here. Now y2, the derivative with respect to x1 is 1, derivative with respect to y2 is also 1, and everything else is 0. So if you continue, you will get a triangular matrix, and on diagonal you have 1, on lower diagonal you have 1, upper diagonal is 0. So determinant of this matrix, because it's upper diagonal is 0, is just the product of the entries on the diagonal, so is equal to 1 times 1 times 1 and is equal to 1. So the Jacobian is 1. So therefore the joint PDF of the output is the joint density of the input at the solution. And remember that this is the solution. So once we, and fx of x is just this one. So I put it here. So it's the product of the distribution. So it's the density of x1 at the solution for x1, density of x2 at the solution for x2, density of xn at the solution for xn, and divided by 1.